Alright, welcome to Exponent Rules. So in this video we're going to take a look at the 6 different major exponent rules. And really our goal is to be able to rewrite an expression so that we don't have a negative exponent, and that any pieces that should be put together, we can do that. So we're going to start off with a negative exponent rule, which kind of forms the foundation of a lot of the stuff that we're going to do. So we start off with the first few examples here. We'll kind of work those out and then generalize a rule. We have y to the negative fourth, which, using the negative exponent rule, will turn this into 1 over y to the fourth. I've got 3x to the negative 2. The x has the negative exponent, the 3 doesn't. So when I'm using the negative exponent rule, I'll get 3 over x squared. And same thing here, when I've got 2x to the negative 3, it would make it 2 over x to the third. So here's the main idea with the exponent, or the negative exponent rule. What it's going to do is allow us to move the part that has a negative exponent to the other part of the fraction. Technically, y to the negative fourth is y to the negative fourth over 1. 3x to the negative 2 is 3x to the negative 2 over 1, and so on. Using the negative exponent rule to make it positive, we move it down to the other part of the fraction. If we had something like this, 5 over x to the negative, fourth, because it's in the bottom part of the fraction, if we were going to use the negative exponent rule, we would move that up to the top, giving us 5x to the fourth. I wanted to show you that it doesn't happen that often. Usually when we have a negative exponent, it's already going to be in the numerator. We'll bring it to the denominator. Our second rule is the zero exponent rule. This is one of the easier ones to use, but we have to be careful not to overextend it and overuse it. The first thing I want to look at is the first one is 12 to the 0 power. When applying the zero exponent rule, will give me 1. Weird. Then I take this quantity here, 7x to the third, y squared, z to the fifth to the 0 power, and I get 1. And the third one, you might think our answer is going to be 1 because it seems like everything's equal to 1. But that only happens when we have a quantity taken to the 0 power, and only that quantity taken to the 0 power. So here the whole thing was taken to the 0 power. Here the whole thing was taken to the 0 power. But on this one, it's not. Only the x is being taken to the 0 power. So that part turns into a 1. The 27 doesn't. We take 27 times 1, which would give us 27. So the zero exponent rule is going to tell us that if you have a quantity taken to the 0 power, it becomes 1. But only that part. Multiplication rule. If we are multiplying quantities with the same base, so x or y or whatever letter we're using, or number for that matter, we can quickly find the simpler version of it. I'm going to work these out and then explain what the heck I'm doing here and where I'm getting them from. These simplified quantities, the way we're getting those is we're taking those exponents and adding them together. So when I have x squared times x to the third, simplified down, that becomes x to the fifth, because I've got x squared, 2, and x to the third, 3 exponent. Putting them together gives me an exponent of 5. And here's the tricky part. Why does this work? Well, if we did x squared, that's really x times x. And if we had x to the third, that's really x times x times x. So if I were to multiply those things together, I would have x times x times x times x times x. I would have 5 of them all together. So this rule that we're using is really a shortcut of this expression here, using the x times x times x times x times x. It's a shorter way to do it by just adding the exponents together. Now, if we're going to divide, our rule is almost the same, except instead of adding, we're going to subtract our exponents. So I have y to the 7th and then y to the 4th. If I were to subtract those exponents, because I'm dividing them, they're the same base, 7 minus 4 would give me 3. Tricky part in this one, I don't have an exponent written on x. It doesn't mean it's not there. It's actually a 1. I mean, just think of it this way. If we were to write a 1 on every single thing that didn't have an exponent, that would take us forever. So simplifying those down, x to the 12th over x would be x to the 11th. All right, so we've got two more rules, and I think these two are very much related to each other. So if you know the one, you probably know the other one. The first one is the power to a power rule. So we're taking something in parentheses and we're raising it to a power. So let's kind of go through how we really do this and then the quicker way. X squared taken to the fourth power. This would really mean x squared times x squared times x squared times x squared. That's what taking something to the fourth power means. So if we want to put it together, what we could do is understand that this is a multiplication problem and they have the same base. So my quick, easy way to do it is to add up my exponents. I can take the 2, the 2, the 2, and the 2, and that would give me x to the 8th. But there's got to be a quicker, easier way to do this. Let's find out. Y to the third to the fifth would be y to the third times y to the third times y to the third times y to the... I'm getting boring writing y to the thirds, but we have 3, 6, 9, 12, 15 of them. That would give me y to the 15th power. And so you might be spotting that there is an easier way to do this. Instead of expanding all that out and adding our exponents together, the easier way is just to take the exponents here and multiply them together. X squared to the fourth becomes x to the 8th. And y to the third to the fifth becomes y to the 15th. Again, exponent rules are a shortcut for a long way of expanding it out. It makes it a little bit easier for us to use them. So the related one is the quantity to a power rule. It's effectively the same thing, except you're going to have multiple pieces inside the quantity. So you're going to have an x squared and you're going to have a y to the third instead of just either one of them. So instincts probably tell you, I'm hoping anyway, that if you got something like that, x squared and y to the third, that you can just take that 3 and distribute it to each piece, and that is absolutely correct. So 2 times 3 is going to give me 6, and for the y's, I'm going to have 3 times 3, which is going to give me 9. Let's talk about this one. This is where we're going to make a mistake. Let's face it, right here with that 3, it's going to mess us up. Common mistake is to forget to take that exponent and distribute to the 3, or do it wrong. Sometimes we multiply 3 times 2 instead of use the exponent. So my recommendation is if you know you're going to use a power to a power rule or a quantity to a power rule, and there is no exponent written, then write it. It's an exponent of 1. That way you don't forget that you're distributing exponents, not distributing the 2 to the base. Different expression, different pieces. So when I distribute the 2 to the exponent, it becomes 3 squared, x to the 10th, and y to the 2nd. Can't do anything with the x to the 10th and the y to the 2nd. 3 squared, though, I'm going to turn that into a 9, giving me 9x to the 10th and y to the 2nd. Simplified down all the way that we can. Again, we can't put things together that don't have the same base. So the x and the y, they're just there right next to each other. There's really nothing we can do with that. So those are our 6 basic exponent rules. Again, it gets more complicated when we start putting things together, multiple rules at a time, but that's about the best that we can do.